So basically, we would like to highlight this at this point, the virtual memory. What's exactly a virtual memory? Why we need the virtual memory? How we can handle the virtual addresses, and so on and so forth. So we can use the main memory as a cache for the secondary disk storage. And these things will be managed jointly by the CPU and the operating system. So in this case, we will have the CPU like that. We will have, or we had the cache like that. We had also the main memory like that. But we are adding also that we have actually the disk. We already also explained that CPU first will try to access the cache to see if the data that is required is in the cache or not. If it is not in the cache, so this means that it missed, and then it will go to the main memory to find if the data is available in the main memory or not. But the question is, what will happen if we did not find the data in the main memory? If we did not find the data in the main memory, so basically we have to go all the way to the disk to grab the data. Copy it to the main, copy it to the cache, and then begin to interface with that thing. You are also can think about the same idea between the cache and the main memory can hold between the main and the disk. In another sense, the main memory can be used as a cache of the data that is inside the disk, or we can cache some of the data that is inside the disk in the main memory. So we can apply actually the same thing. Programs share the main memory, and each will get a private virtual address space holding its frequently used code and data. So this is something that is very important in order for us to use the virtual memory. And this will be protected from other programs. We also would like to translate all of these virtual addresses to physical addresses. So there will be like a virtual addresses that exist nowhere, and we have a physical addresses. And we would like to translate these virtual addresses to the physical addresses, as we will see shortly how we can do that. But before we move forward, we would like to be aware of these couple of expressions. VM block, virtual memory block. From now on, in the virtual memory case, we will call it a page. Virtual memory translation miss, the miss will call the page fault. So the block now will call the page. And if I miss that page, I will not call the miss, I will call it page fault. So this is basically these two expressions. So as you can see from here, we will have a virtual addresses, one after the other, and I will have the physical addresses. And these virtual addresses, some of the blocks or the pages will refer to a certain particular page inside my physical memory, or it can point out to data inside my disk. Each program inside the virtual memory will have a certain particular location that can be used for that particular program with that particular addresses. That is point out to a certain particular addresses inside the main memory. The nice thing about that we can actually share the main memory among different programs. So basically, the CPU will try to search for this page, for instance. It will go to this, it will find that this virtual addresses refer to the main memory. In that sense, I found my data in the main memory and there is no page fault. But it, for instance, went to a page or a block that is inside the virtual memory that refers to the disk. So this means that I already have a page fault. And according to that, I have to fetch the information from the disk, copy it to the main memory. Then the question is how we can control these actions. First of all, how I can refer to a certain particular page here using this address scheme. Assume that we have from 0 all the way to 31. So we have 32 bits to address all of these locations inside the virtual memory, which exists nowhere. There is no existing, it's just virtual. How we can use that to do this particular process? They said that, okay, there is something called page offset and there is something called virtual page number. And the page offset will be responsible for 0 to 11. So we have 12 bits that is corresponding to the page offset. The rest of the 32, which is 20 bits, will refer to the location inside the page number. Well, what does that mean? Meaning that I will use these 20 bits to address which page I need. Let's say, for instance, I am targeting this one. Let's say address 100, for instance. After I went to address 100, let's zoom in to that block. That block or that page is like that, and actually we have a lot of data. How to address the data inside that page? This is what we call the page offset. So I have 12 bits to address the data inside the page after I have addressed from here. So first, I specify where is exactly the page, which page number. After I allocate the page, then I will look inside which offset do I need. And from here, if I'm asking you how many different locations I might have in the virtual addresses, you can easily say you have 20 bits, so it is 2 to the power of 20. In another sense, I'm giving you 3 bits to address like the number of floors inside the hotel. And I'm asking you what is the maximum number of floors that you can address with 3 bits? 2 to the power of 3. What is the maximum number of floors that you can address if you have 20 bits? 2 to the power of 20. But then after you arrive to the correct floor, then how many bits, how many rooms you can address in that floor if you have 12 bits? You will have 2 to the power of 12 rooms, correct? If I'm asking you, given this information, what is the total size of rooms inside that hotel? So you have 2 to the power of 20 different floors, and in each floor you have 2 to the power of 12. What you need to do is multiply this by that, correct? So basically, in order to know what's exactly total here, it will be 2 to the power of 20 multiplied by 2 to the power of 12. But this, by the way, will give us the same things if we are taking this, call this as 32 bits. And if you have 32 bits, I'm asking you how many different locations that you can address. This 2 to the power of 32, which is also equal to 2 to the power of 32, because you took at the end of the elementary school, as far as I remember, that if you have the same base, you can add the power, correct? So it is the same thing. But I have just like described here conceptually how we can break down these numbers. The same apply for the physical addresses here. For these physical addresses, in this example, we have chosen that instead of having, as usual, 32 bits, we have only from 0 to 29, which means that we have only 30 bits. 30 bits, this is for my physical addresses. I will take out of these 32 bits, the 12 bits offset as before. The rest here will be 18 bits. If I'm asking you how many floors do we have in the physical addresses, or how many pages do we have in the physical addresses, with the same idea, it is 2 to the power of 18. But if I'm asking you about the total size of the physical address, each of these pages or each of these floors contains again 2 to the power of 12. So I have to multiply 2 to the power of 18 multiplied by 2 to the power of 12 will give you the size of the cache, which also it is 2 to the power of 30. But the question is, why this is equal to that? Why I have always to take the page offset the same? So back to this example, I told you that with this guy, with this virtual address, I might go to a certain address that is point out to a physical address, or I might go to a certain particular page that is basically exists in the disk, correct? But remember that if this guy is basically exists in the physical address, so this means that it has to be exactly the same size. Location-wise, it might be different, but size of the page need exactly to be the same. For instance, this guy is in location 0, which actually point out to this guy, which is location 0, 1, 2, 3, 4, 5, 6, for example. So 0 is pointing out to location 6. But this does not mean that basically the size is different. The size is exactly the same. So if you zoom in into that, and if you zoom in into that, the size is exactly the same. Okay? But the number of floors that is basically existing in the virtual address, it is not the same number of floors or pages that exists in the physical memory. Which does make sense because actually we expected that from the very beginning. I told you that inside my virtual address, some of my locations will be belonging to the disk, not the physical address, not the physical memory address. So you know in advance that the hotel of the virtual memory will contain more floors than the other hotel, which is the physical memory. You can think of this as two hotels. One, for instance, like has 100 floors, the other has 10 floors. However, I am telling you in advance that either this or the other needs exactly to have the same amount of rooms inside the floor. So if for instance, the one that has 100 floors, each floor has 100 rooms, also the second one that is 10 floors, each floor need to be exactly 100 rooms. Here is exactly the same. So they have not totally different, they have not exactly total number of pages, but the page size itself is exactly the same. And if the page size itself is exactly the same, I have to have the offset here equal to the offset here. Because this will point out where is exactly the data inside my page, which will be exactly the same inside my physical. So as soon as I arrive to the page, then they will be exactly the same size, and I will point exactly the same offset. Is that clear? So let's just like to review this information again. So the page size is 2 to the power of 12. Why? Because the offset here is 12. So how many rooms? 2 to the power of 12. This is the page size, which I already mentioned when I zoom in here. This guy here, I have 12 different bits, so it will be 2 to the power of 12. The number of physical pages allows in the memory is basically 2 to the power of 18, because this is what we mentioned here. So 2 to the power of 18 different floors here. The number of entries in the page table is 2 to the power of 20, because this guy is basically 20, so the number of floors here will be 2 to the power of 20, or 1 million entries. So the main memory can have at most 2 to the power of 30 bytes, because we have 30 here. But also we can calculate that differently by multiplying 2 to the power of 18, which is this, multiplied by 2 to the power of 12, which is this, 4K. This is exactly 2 to the power of 12. 2 to the power of 12 multiplied to 2 to the power of 18, it's equal to the power of 30. The virtual address space, we can do exactly the same, and it is 2 to the power of 32, so it's 4 gig instead of just 1 gig. So now with these virtual addresses, I can basically have a shared memory inside my physical by using different programs inside my virtual address that is basically will locate or will point out to different locations inside my main memory. But the question is, okay, so we already explained briefly that there is something here that is actually point to another thing here, and so on and so forth. But how we can do that? First. Second, what will happen if I went to this page, for instance, and I didn't find it, so I miss what I should do, which means that I have a page fault. What exactly would be the situation in this particular case? So in page fault, the page must be fetched from the disk. But unfortunately, this will take millions of clock cycles. But again, we will try to minimize the page fault rate. How? By exactly the same idea that we had earlier between the cache and the main memory, because now we will apply the same concepts. Instead of between the cache and the main memory, we will apply between the main memory and the disk. Again, this is the CPU. Here we had the cache. Here we had the main. Here now I have the disk. If, for instance, I would like data here and I didn't find, I have to access the disk. But also with this mapping, I can use fully associative placement, and I can use smart replacement algorithm, for example. We have covered like some replacement examples earlier, which we will also highlight again this time. So we have answered the first question. If we miss, what exactly we will do? Second, the question is how we are doing this translation. Translation using the page table. So I will have, again, my 32 bits virtual addresses, and I will have my 30 bits physical addresses. The offset here is 12, the offset here is 12, this is here is 18, this is here is 20. How I can transfer an address that is here to an address that is here? They said that, okay, we will have something called page table. Inside this page table, I will have different locations. And according to the value inside my virtual page number and what the page table register refers to, we will be able to allocate a certain location. So I would like again to highlight that the page table register is just a register that is inside the CPU. And these registers will be used by the process that is handled at the moment. And this register, page table register, will point out to the beginning of where exactly I need to calculate my virtual address. In another sense, if I would like, for instance, to target this location, this guy will refer to this location at the beginning. This guy will refer as how much I need to add. So for instance, if this is refers to location 2 and this is refers location 100, so this guy will be 102 as an example. After I arrive to address 102, so I will get that particular data. This data that is inside this particular location is 18 bits that is referred to where is exactly you will find that inside the physical address. So instead of just giving you the physical address, I'm asking you to go to another location and then open that mailbox to know exactly where you should go. Secret agent. Yeah. So we cannot tell you everything just like as the normal way. We have to loop around. Again, this guy will let me know exactly where is the virtual address. This guy will know or will let me know exactly where I should begin. This plus that, for instance, I arrive to this particular address location. After I arrive to this particular address location, this guy will have the data that is belonging to where you should find your physical page number. So this is might be location 102, as I already mentioned, but the data that is inside here might be 1000. And this 1000 means that you have to go to the physical memory to address 1000. Then now go to address 1000 inside the physical memory. So the 100 that it was here now referred to address 1000 as an example. Okay? So this gives us an indication that a process can has in its own virtual address a certain particular value. In another process can has in another place the same exact value, but both of these values will not refer exactly to the same location. What does that mean? For instance, if we have this 100 here and another process is using the virtual memory and inside a certain particular slot, it's written there 100 also. But 100 plus like where you will begin, as an example, will give you another slot. So you may reside here. If you reside here, so this means that you are pointing out to a totally different physical address location, even though you have the same address in the virtual memory. And this will be the beauty about that. The page offset here and the page offset here, as we already explained earlier, needs exactly to be the same. Where is this located? This is located inside my main memory as well. My page table is located inside my main memory. So again, this is my page table. I will point out to a certain particular location according to the virtual page number. If this location has an address that is pointing out to the main memory, then I hit the main memory and everything will be okay, or not totally okay, of course, like the cache, but at least it's better than the disk. If, for instance, I did not find the data that I am pointing to, I arrived to that particular address, and this guy contains the data inside my disk. Unfortunately, in this situation, I will have a page fault, and if I have a page fault, this means that I have to fetch all of the information from here to my main memory. But unfortunately, in this case, I am consuming a lot of time, millions of cycles, delay or wait. But what exactly we'll do in terms of the replacement and write? Of course, as we already explained earlier, to reduce the page fault rate, we can use least recently used replacement policy. We refer to that as the LRU. So the reference bit inside my PTE can be set to 1 if I access the page, for instance, but this will be cleared to 0 by operating system periodically if it is not used. A page with reference bit equal to 0 has not been used recently. Unfortunately, this disk writes take millions of cycles. And because of that, write through, of course, is not practical at all. Instead, we can use the write back. Because if I will use the write through as we have described earlier, this will take a huge amount of time just waiting until all of the information will be written in the disk. But by using the write back, unfortunately, I will relax this a lot. But the most important thing that I have to take into consideration, again, my dirty bit. As you can see from here, the same concept that we have applied between the cache and the main memory, we are now applying between the main memory and the disk. But the question is, unfortunately, with the scheme that I have already described, this will take, in the best case scenario, a lot of time. Why? Because going back to this, let's see here. So this is the CPU, correct? The CPU will go to the page table, try to ask for a certain particular place to know where is exactly in the physical memory. But this by itself, I am searching in the main memory. So I'm searching in the main memory twice, in another sense. With this physical memory, this is the main memory. This page table also inside the main memory, by the way, but in another location. So if, for instance, I did not find the stuff that I would like belongs to an address here, as we mentioned earlier, I have to go and fetch, which will take like millions of cycles. The best case scenario that I will target this guy and found that it is belonging to another address inside the main memory. However, even with this best case scenario situation, I am losing a lot of time. First, in order to arrive to this, Second, in order to arrive to this, we already explained that by contacting the main memory, I can actually allocate cache in between, correct? And this is what we exactly covered earlier. The question is how we can apply the same idea here. Again, with this main memory, we have the cache, so always I will try the cache before the main memory. Can we apply the same idea here as well? So instead of having the whole page table inside my main memory, can I take the frequently used locations of that particular page table into my cache? I can do that. So I will create a cache here that will basically have this table shrink it, the frequently used data only in that table. And then if I found it there, that would be perfectly fine. And if I found it there, let's see like what will be the scenario. If I would like to access something in my page table, but I have my cache here, and this table, I will call it another things. So table, but for the cache. This guy has the cache. Here is my CPU. The CPU at the very beginning will go to the cache here. I might hit or miss. Let's say like I hit. Okay, so that's perfect. Then this guy might point to the cache. So I again hit. So hit. That would be the best case scenario. Correct? Second, I might hit here. So I found that it is here, but this is actually the address that is needed is actually here. So it is hit miss. Because when I went to this, I did not find it. So I found it here. So hit miss. Correct? So this is a little bit second worst scenario. Let's say it that way. Another situation that I might not hit here at all. I might miss. If I miss, so this means that I will go to the main memory. And after this main memory, this guy might point out then to a location in the main memory, or it might point a data in another place, which can be also again a miss or a hit. But still we have even a worst case scenario. The worst case scenario that actually I miss here, I went to the main memory, I found that actually I'm pointing out to this location. This location means it is neither in the cache, nor in the main memory. It is in the disk. So I have to go all the way to the disk to grab the data to the main memory, and this will be the worst case scenario. So again, just to summarize that, I will create something called translation lock aside buffer, TLB, that will be inside the cache. My page table entries, the PTE, will be inside the main memory as we have described earlier. This is typical 16 to 512 PTEs, 0.5 to 1 cycle for hit, 10 to 100 cycles for miss, and the miss rate is something like that. We can do better by including this TLB, as you can see from here. So now I have this page table in my main memory. This is also in my main memory. The virtual page number will point out to a certain address in the TLB, which is inside the cache, but in parallel will point out to a certain particular address inside my page table inside the main memory. If I found it here, whatever, after comparing the tag, if I found it here, whatever I need, so I hit, and no need to wait for the main memory. Because basically, if you remember, just like for instance, if the access time for the cache is 5 nanoseconds, but the access time for the main memory is basically 50 nanoseconds. I have sent the two addresses in parallel, but one arrived after 5 nanoseconds, so I just neglect the one that is 50 nanoseconds. I don't have to wait because I have already received what I need. Correct? So in this case, I hit. If I did not find, I have to wait for 50 nanoseconds. If I wait for 50 nanoseconds and I was lucky that I have arrived to a place that is belonged to a certain particular place inside the main memory, so that will be good. But if, for instance, I have arrived to a place that is corresponding to a data that is inside the disk, so this means that I have a page fault. And in that case, I have to go all the way to the disk to fetch all the data to my main memory. Okay? Is that clear? So if we have a TLB message as we have described, load the PTE from the memory and retry, and this could be handled in the hardware. If the page is not in memory, so this means that the page is fault, and then I have to fetch the page and updating the page table. The replacement, as we have covered earlier, that we can use the least recently used mechanism, but this is unfortunately is complex and costly in terms of the hardware. We have also described something else that is the what's called random. This is in performance close a little bit to the LRU, but it's easier to implement. With the virtual memory LRU approximation, of course, with a hardware support.